Hello everyone. Good evening to all. I Sahil Gaurav, Chair of the Industry Application Society Student Branch Chapter IIT Guwahati. I welcome you all to this distinguished lecture that is provided by Professor Rajesh Kumar. Before we begin the lecture, let me give a short introduction about him. So, Professor Rajesh Kumar received the BTech degree in Electrical Engineering from NIT Kurukshetra in 1994, the ME and PhD degrees in Power System and Intelligent System from the MNIT Jaipur in 1997 and 2005 respectively. He was a postdoc research fellow with the Department of Electrical and Computer Engineering, NUS Singapore from 2009 to 2011. Currently, he is working as a professor with the Department of Electrical Engineering, MNIT Jaipur. His research interests focus on intelligent system, data-driven algorithms, and analytics and smart grid. He holds 16 patents, patent publications, and published more than 600 research articles in international conferences and journals. He has received, he has supervised 25 PhD, more than 50 master theses. He is recipient of several academic best papers, best thesis, and professional awards. He has received the Career Award for Young Teachers in 2012 from the Government of India. He has delivered 200 plus keynote expert talks in various faculty development programs and workshops. He was conference program chair PDS 2018, general co-chair ICRAI 2018, IC IICP 2018, ICPS 2019. He was the general chair for PDS 2020, AISCC 2020, GCAIA 2020, PDS 2022. He has been an associate editor of IEEE ICS, IEEE IT Industrial Electronics Technology News, Swarm and Evolutionary Computation, Elsevier, IET Renewable and Power Generation, IET Powertronics International Journal of Bioinspired Computing, and CAAI Transaction Intelligence Technology, IET. He was IEEE Counselor, MNIT Student Branch, founding faculty advisor, IEEE Student Chapter at MNIT, Honorary Secretary of IET Rajasthan Chapter, EXOM IEEE Delhi PES IES, and Vice Chairman IEEE Rajasthan Subsection. So now I'm handing over to you.
Yeah, thank you, Sahil, for introducing me to the fellow listeners here. I hope my voice is clear.
Yes, sir, it is audible and it is clear.
Yeah, okay. So good afternoon from here. Right now I'm at University of Johannesburg, and good evening to the participants there in India. Let me share the screen and then we can have discussions. Okay. So is the screen visible to everyone?
Yeah, yes, sir. It is clear.
Okay. Yeah,
It is
thank you very
visible.
much. So friends, okay, yeah, again, I welcome you all in this session here. And for next 1 hour, we are going to discuss something towards uh, that intelligent power management and the control of electric drive using reinforcement learning. So yeah, what I have done here is uh, divide this whole discussion into few segments. First part, we try to understand the terminologies which are being used in reinforcement learning. That what are the various terms people are using it, and then how those things can be used further to develop the algorithms. Then the second part of it, we talk about the various algorithms which are available there. We start with like, okay, what how the algorithm works, and then what are the we discuss upon the assumptions, and then what are the issues, and then how people modify from one stage to another stage. And in the third part, I'll discuss a few of the case studies where we have implemented this thing. This is now getting a very popular approach to solve different kind of problems. If you search it out, you'll find a lot and lot of problems can be solved by this approach, and people are using it. Uh, and followed by the last 5 or 10 minutes, if time permits, we'll have a Q&A session so we can have a discussion on some your observations or questions you have. Okay, so let me start with this one. So we start with reinforcement learning, and we know that we do a lot of learning. We'll do a lot of AI part there. So one part is basically isolated decision making. That means we have certain kind of a data, and then from that data, we make our model learn. And then we do two types of job there. Either we do classification of the things that it belongs to a particular class or not, or we do some kind of a regression. We try to predict certain kind of a value there. While doing this one, what is there, we need a lot of data, and we need the data which are labeled data. That means we know that corresponding to this input, should be the output, and we propose a model which map your input output correctly, and that is exactly what we do in supervised learning there. Uh, but think of a scenario when your data or decision making is not isolated, or it's a sequential decision making. That means every action has certain kind of a sequence, and that sequence is action and the state, and then action and the state, they are interrelated with that one. So if such kind of scenarios are there, and a lot of real world things, we will find that such kind of things exist there. Typically when we talk about electrical people, we talk about the control part. Yes, we know that there is a certain kind of state, and then we take certain actions, and likewise. But it has a lot of if you figure it, search it out, lot of such kind of scenarios, you'll find that where we have sequences there. So for such kind of scenarios, we go for reinforcement learning, and reinforcement learning has a very good, strong mechanism, that is the feedback mechanism. So this feedback mechanism keep make you learn every time. So you get a feedback on the things, and then you keep on modifying the things and accordingly, and then you can shape up your model there. Obviously, this is more towards a sequential decision making. So that's a good part here. Your training data is self-generated. It's no more like what we do in a conventional supervised learning, that we need a lot and lot of data. And that is basically a very big challenge if you go for supervised learning. Every time we stuck up with the data basically. So we need a lot and lot of data, and that data should be labeled also. So there's a challenge here, but here the training is self-generated, and that's a good part here. So let's understand what are the components of the reinforcement learning. So first component is basically an environment. So environment is let's understand how it works there, and by understanding that, we'll understand the components there. So environment is something like that. So see how I learned to play a chess game. So that is a simple way to understand it. So so there is a chessboard, and there is another opponent player, and you can see there are black components and white components. So so some basic information is known to me, that okay, you can move this one like this, and you can move this component like this. That information I have. But the point is how to make a strategy, or how to win the game. So this thing, this the chessboard in front of me, this is an environment basically. So that is one thing. So on the extreme side, you can see this is an environment for a problem, where you can see there is a fire, there is some kind of a battery. This is kind of an environment, means this is a grid environment there. And then what we need is, I want to learn the chess, means I'll work on that environment. Okay, so that is, we call it an agent. So here in this problem, we are taking one agent, which is a robot there, which is there on your screen. So these are the two things which are required every time when you want to implement reinforcement learning. So if the environment is there, and I want to learn the chess, or there's an agent there, I treat myself an agent. What I'll do, and the first thing is, I'll get some observations from the environment. Those observations are in terms of some states. So that is the first thing which we require in reinforcement learning. That is basically, what is the state of what is my state. So here in your grid problem, your robo can be at any position, like here, or it may be here, or it may be at any position. These are known as the states basically. And once I know the state, I know the arrangement there, then what I'll do, I'll take certain action. Okay, so I move, I'm playing with the black component, so I move one of the component, say the elephant or some other component there, uh, to certain extent. So that is my action. In this robo problem here, you can see there are four actions: going back, going front, going up, and going down. So these are the four actions. These are defined. I have defined these actions there. So there in game also, some there the actions are defined. The how much you want to go, that is a different part, but we know that each component has a uh, defined action. Okay, and then when I take an action, so I'll take an action on the environment, and then what we'll do is environment give me the reward. Because if I move one component, there are possibilities. One possibility is that I'll kill the opponent component, so I'll get some kind of positive reward because the ultimate goal is to win the game. The second, nothing will happen, so there is no reward as such. Third, it may be possible that I move my component and it will be killed by the opponent in the next step. So that's basically negative reward of it. So reward is always, so you can say we represent states by S, actions by A, and reward is basically we'll get uh, certain kind of value which help us in moving further or taking decision, and it always depends upon three things. So what are those three? One is what is my current state, what action I have taken, what is the next state I'm reaching, and from there I'll get a reward. So these are the three basic components which you'll find used commonly when people talk about reinforcement learning. And what is the goal? And the goal is we need to learn a policy. We need to learn some kind of action plan so that we maximize our benefit. So that is the basically our goal. So how we define policy? We define usually policy by pi here. So we need this mapping that, okay, what will be the action plan of how I reach to different states so that I get the maximum reward. Well, those things we execute on an environment, and how you model an environment in reinforcement learning. One way is we can use Markov decision process. Markov decision process is used to model that environment. And there are a lot and lot of applications of this whole approach. You can find it in robotics, games, autonomous driving, sports, business, healthcare, intelligent control. People are now, yeah, they are exploring various domain in bioinformatics and many more there. Okay, so what are the takeaways from here? We need to develop a Markov decision process because that help us in developing the understanding the or modeling the environment. And we need to develop a policy. The policy is a learnable policy. So we have to learn a policy which is optimal. Optimal means which give me the maximum reward. Okay, fine. So we have these things with us. So we are discussing a few things. Those are the components. We have discussed what are the states. We have discussed what is an action. We have now the next thing which is important, that is a transition. And transition means like, okay, your object is somewhere here, how it move to the next state. That is basically the transition. Okay, so that is the transition. Transition means moving from one state to another state. And how it will occur, there are different ways. So one transition is deterministic one. Deterministic ones means my robo is here and I give this command that go down. Okay, and at 100% it means like it will go down. That is a deterministic because I can I can check it in future that, okay, if this is a command, where will be my robo. Second kind of a transition is stochastic. So stochastic can be like this. I ask the robo to move down and you'll find that robo maybe remain there itself. It may go left, it may go down. So that is stochastic because I don't know after giving the command whether it is reaching there or not. How to model it? Okay, obviously here we associate probabilities. That what is the probability I give a command to go down and it will go down and something like that. So this is the way to represent the probability. Okay, so probability is this one, like, okay, you are in state S, okay, and then you take an action A. So what is the probability it will reach to the next state S dash? So like here in this problem, when we'll solve this problem, so I'll try to connect it with a numerical so that we can understand it nicely. That we are in state S and we have choose taken some action A. Action A can be left, right, up, down. It can be anything. So 90% it will follow the action and it go to the next state. But it may be possible that 10% it remain there itself. So there is a probability associated it. That is 0.9 is a probability it will go, it will follow S, A, S dash. But zero point 0.1 is a probability that it will remain, that is S, A, and S there itself. So that is basically the another term which is required. This we need it because in the real world, you'll find that things are stochastic, nature is there, and we need to fix it. Then reward, we already discussed that what is the reward. Okay, so the question, the thing is basically the dynamics of the environment is not actually known to us. If the dynamic the environment is known to us, then we can go straightforward with the deterministic. There's no need of a transition, but probabilities. But the dynamics of the environment is not known, and that's why we are going for it. And what is the optimal? What is the ultimate goal? Again, I repeat it. So we need to find out the optimal policy. Okay. So this is the search tree. How it will work? Let's understand the search tree. You'll find all the terms in one. So uh, uh, I'm at state S. Okay. Now state S can have can you can see there are many options. It can take this action. It can take this action. It can take this action. Now there are different actions, and what we call it, each action is basically a policy. At any instant, I can I can decide upon that. Okay, which action I have to take. So here in this figure, you can see there are three actions there. So these are the three different policies, and policy vary from person to person and gamer to gamer. Like, okay, take it a case that you are a soccer coach. So your policy can be that, okay, first half you defend and second half you attack. For the next team, your policy can be different, that okay, no, attack from right from the beginning. Once you score over the other team, then start defending it. So it's a different policy. So there can be many policies. Each policy defines certain actions, but the ultimate goal is we have to find out that policy will which will give us a maximum reward. So this one is basically policy. So I choose this action following by policy pi. So this one is pi. Okay, so I choose this action. Once I choose this action, then there is a probability associated. You can see that is a probability associated means there is a probability that it will go to S dash because of the transition. So that's why we have written that given an S and taken an action A, what is the probability, or what is there is a probability associated to reach S dash. So it will move here. Once it reaches here, you will get a reward. So this one is the search tree. So you are here, you have chosen one policy, you have taken one action, and then based upon that, following a probability, we reach to a new state and we will get a reward. This is how the process occurs. Then again at S dash, we take another action and then move on. That is how it will move. So how this is the way we move step by step. But uh, but this policy what is there may be optimal, may not be optimal, and goal is to find out the or learn the most optimal policy. So what is the most optimal? Okay, maximize your reward. So okay, when you are in state S0, when you are at S0, you have this reward. Then the next time step you have this reward. Next time have this reward. So what will happen? What is the way? Good way is just okay. You sum of them all, and whatever is the return total, that is the total reward. Let's maximize it. Well, if you follow this one, may not be a good idea, because because of certain kind of issues. Okay, so issues can be, what can be the issue? You can let's understand in that way, that okay, say I assign this state as a value 1, this state also as a value 1, this state as also 1, all these initial states as 1, and say last one is okay, here it is written +1, but even if I write down +5. So if I follow this technique only, what will happen? Have that okay, this bot come from state 0 to S1, it will get a reward of 1, then it go back again reward 1, and again come back again 1. So it keep on oscillating between those two states. Why it will move further? Because every time it move, it will get a positive reward. So, and we are saying that okay, we want to maximize, we will maximize the sum of the rewards. So that's the problem here. So what is the way out? So there are few solutions to it. First, okay, what you can do is you fix the termination, that okay, after 10 steps or 20 steps, stop it. That can be one of the way, but may not come out of this solution. The second one is, you can say there is a absorbing state. If you reach to the absorbing state, it will stop. Well, if it reach to the absorbing stage, only in that case it stops. And third one is, this one is more appropriate, that is discounted reward. So what is the discounted reward? Means that whatever reward you get immediately, that will be the highest, but if you move on, the reward keep on reducing, and that ensure us the convergence of our problem. Okay, so that is basically how that it is meaning of discounted reward. You can see here, this is my immediate reward, and this one I'm putting a discount factor. Next step, then discount factor square, and we take this discount factor less than 1. So you'll see that if it is less than 1, and if we go for the powers, you will find that after some time it converges. People have given some proofs mathematically. Yes, it converges there. Okay, so this one is just a bounded return, but the important part is here. This one is very important part, the gamma. So if my gamma is basically very small, that means this value is very small. So I focus only on here. Say it is 0, so so nothing will be counted on this side. Only I focus on the immediate one. And if gamma is high, then I believe on future rewards. This is very important aspect here. People connect it with the financial part, but just think of a medical problem. Okay, so you are customizing a treatment for a patient there. So patient comes to you, you are a doctor, and he explains you that okay, suffering from this problem. And the thing is, now you have some solution for it. So there is a treatment, there is a medicine, but this medicine has a side effects in long run, but it will cure the problem immediate kind of thing. So that is basically the gamma role. So immediate reward is very high, but it has certain kind of uh, problem or side effects in future. There is another medicine which may not correct the patient immediately, but there are no side effects or less side effects. So now you have to choose it, and that is exactly what is the gamma here. That you want to get immediate reward, or you want to look for future rewards also there in your calculation. So that is basically the gamma here. But this one is also again not very sufficient to find out the optimal policy. But somehow, if we put it this gamma into calculation, we ensure it will converge to certain kind of a problem there. Okay, so these are the standard notations. You are at any state, you have taken certain actions, and then state action, and keep on moving. Okay, so now to calculate the values, what we do is we calculate the value of the state under certain policy. We follow certain policy. Okay, and we follow a policy, but we know the environment is not completely known to us, not fully observable. There are issues, so we'll say that there are certain expectations we connected here. You can see that there are expectations on the return given starting with state S and we follow a policy pi here. So that's the meaning of this term there. Okay, so we can represent it like this now. So what we have done, interestingly, this one is my immediate reward. This one is discounted future rewards. Okay, if I multiply it by a probability of that movement, and so that will give me my expectations. This term here represents what policy I am following. Okay, so that is basically the value of a state. So you calculate the state value, and then we follow certain kind of a methodology that, okay, if I know the value of each and every state, I can find it out, okay, what is the best action for me. Okay, so so what is the optimal policy? And optimal policy is when we maximize my profit, maximize my rewards. So I put a max of a, so maximizing this rewards there. Okay, so we are following certain policy. We calculate the values, and from there we take that path. If I accumulate all the rewards, that will give the maximum reward. So in earlier one, we are just following, we are only believing only on the states that, okay, what is my state? But it is not good. The good is because at any state you can have multiple actions. At any state, you can see that there are four actions. You can go up, down, right, left, and likewise. So can we put that into it? And once we put that into our calculation, okay, then we call that one as the Q value. That is the quality function. That is a quality value. What is the quality of my that state and action pair? Rest things are almost same. Okay, how to calculate this one? The values. Let's check out some numerically how it can be done there. But before jumping to it, let's understand what are the different algorithms. I'll explain that how those calculations can be done. But there are many algorithms in reinforcement learning. These algorithms start, you can see from this tree. So if you want to, if you start reading in on RL, people usually start from bandits, slot machines, which is not our agenda here. We are more towards MDPs, that is Markov decision process. MDPs can be two types: model based and model free. Model based, in which model of the environment is known to me. Model free, I don't have any prior information or knowledge of the environment. I learn it while doing the things there. So it's not like model on model is known to me. In model based, again, we have two cases. One case is the model is given to you. So it's fine then. So model given to us is basically states, what are the states and what are the transition probability. Those things are known to me. If those things are known to me, we can say that model is given to me. In the second case, model is not given to me, but some experimental data are available. So if experimental data are available, what I'll do is I use some kind of machine learning technique or statistical technique to learn the model that, okay, this is the model, and then I process it. So in both the cases, I have information about the model, but in this category, I don't have any information about the model. If you want to solve it, we solve it by two ways. One way is value based. Value based means, now let's now this is the interesting part of it. Value based means at each step, I focus on the value, that what is the value. I calculate the value by some method, and then I that value give me the information of the reward, and then I connect those different states in such a way that when I complete my whole trajectory, I find out the total reward. And what is my maximum reward? That is the best trajectory I can have. That is basically value based. It is same like if you have played game like Subway Surf or something, Mario, and likewise. So when you run, you get some coin, and likewise you keep on getting the coin and then keep on scoring. It is same thing like that. That is value based approach. The second one is here, which is basically policy based approach. So policy based approach means like I decide a policy that, okay, always I go left side, and then I evaluate it, that if I go always left side, I follow this policy. If I evaluate it, what is my value, and then I change it. I change my policy that no, I'll go always right, and then I evaluate it. So it's basically I only focus. So there are various policies, and I try to find out which policy is the best for me, which will give me the maximum value. So we go further there. Further division is there. So in value based, we have two approaches: own policy and off policy. What is own policy? Own policy means my learning policy and the evaluation policy both are same. That is, if both are same, we'll say it's a own policy method. Off policy means my learning policy is different, my evaluation policy is different. So that is basically the off policy. In policy based method, I told you that I have many policies. I have to figure out which is the maximum. So it's more like an optimization problem. So maximize my policy profit. It's optimization problem. So when we talk about optimization, automation can be gradient based. It can be gradient free. So gradient free means like you can use evolutionary algorithms or some other approaches. Gradient based means like, okay, you go for gradient descent methods and likewise. And these are the various methods people have developed. XRSA, Q learning, deep Q learning, and policy gradient, DRPO, A to C, DDPG, and likewise. So these are the various methods people have developed. This one is just kind of a structuring of your RL algorithm. So let's talk about that as value iteration method and what is the how it can be calculated. It's not that difficult. Mathematically, it may look like that. So this is my equation. Okay, and the agenda is to get these values of the states. So what how we can do it? So initially, let's assume everything 0 0 0 0. Only these two values are known to me because it's fire. It's a termination state -1 reward, and this one is battery. So that robo if reach here, robo can charge its battery. It's a +1. So these are the terminal state. This is a block here. You can see here. This is a block. So it cannot go there. Rest values are 0. So how to get this value? We use this equation. And what is the beauty of this equation here? This equation states that your current value will be something max of some probability reward of the current value and the future value. Well, we use this technique, and how we use it? Okay, we run this robo many times and say at one instant it moves from this place to this place. Somehow it reach from S10 to S11. So then let's calculate it. So how to calculate it? So you say that you see here what is the command, what is the transition probability. You are in S, and if I ask for action A, 90% it goes to follow that action. So that is basically 0.9 here. Initial reward I assume 0, so it is 0 here. Okay, I assume the gamma is equal to 0.9. I put 0.9 here. And what is my next state reward? If it reaches here, it reaches here, it is 1. Plus the second part, that is it will not follow my instruction. So it's a 0.1 times of 0 reward. It remains there whose value is 0. So when I calculate it, I'll get a value 0.81. So this is how I calculate this value here. Okay, so this one is the first iteration. In next, it will change. Basically it will change. You can see here it will change. How it will change? Because this terms remains same, but in the next iteration this is no more 0. This value is 0.81 because you'll get a new value. So this value changes. So we'll get 0.88. And then if this is 0.88, then we can get this value. We can get this value, and we keep on filling this table every time. Okay, so we keep on calculating these values, and finally you'll find that they will stabilize somewhere. This one is just a stabilization curve. And once it is stabilized, now what is our objective? Objective is to get the maximum points. Okay, so I'm starting from here. Okay, this is maximum side. I'll go this side. From here, this is the maximum. I go this side. If I compare, this one is less, this one is more, I go this side. and then compare this side, it is -1 and don't go. So this one is positive, I go this side. Here it is 0.79, I don't go, this is 1, I'll go there. So this is the track, this is the policy, this is the path which is the optimal path for me. So the robot will follow it and will reach here. So either it will go by this or it will go by this. Both are having the same values. Just check it. Once it is stabilized, it may be possible. If it is not there, then obviously it will follow the optimal path. This is how you can do the calculation value based. So this is dynamic programming. We trace it back from the endpoint and go back to the initial state, like in the reverse direction. Okay, so this is one approach which is basically uh, policy, sorry, value based. Uh, and the another approach is basically policy based. So what is a policy based? I decide a policy that okay, I'll always go this direction. Whatever is the value, I'll go this direction. It's fine. Then what we'll do? We calculate the values. So we calculate the value here. So how we calculate the value here? This is 0.81, fine. But when you calculate the value here at 6, you'll get a negative value here, 0.8, 0.81. And then we do the rest of the calculations. Okay, we do all the calculations till it stabilize. Okay, so we do the calculation till it stabilize. Our policy remains same. Okay, once it stabilize, now I check the my policy. So I check, when I check the policy. Oh, sorry. Uh, I want to show you the values there. I don't know if that slide is skipped somewhere or not. Yeah, I think it is skipped somewhere. Anyway, no need to worry on that part. But say this one is the stabilization part. It is stabilized here. Now I check my policy and what is the check here. So if I'm at this state, now I will wait it. I'll say that going this direction is further reducing it, my reward. So not a good way to go in this one. Going up, it increase my reward, fine. Going down is further increase my reward. This one is better, much better. So I'll change my this direction of going in this direction. I'll go in this direction. That is basically when once I evaluate my policy, I update my policy. Okay, so that I'll do it after stabilization of this one. So this is basically policy improvement. I change my policy, and the time I change my policy, this value changes. And once this value changes, and when I redo the things there, I'll find that after some time it stabilizes again. So this is the difference between the two. One is policy based iteration, another one is the value based iteration. Okay, so you can compare both have certain kind of benefits and advantage and disadvantage. But the part here is both approaches are very simple. The convergence is very fast, but there is a problem, and the problem is it needs the knowledge of the environment basically. Okay, and most of the natural problems, the model is the knowledge of the model is not available. It may be partially available, but complete knowledge is not there, and that is one kind of a issue that these people think of shifting from this approach to another kind of approach there. Okay, so they talk about the Q learning, and Q learning is the quality learning. And what is there in the quality learning? Quality learning is basically it depends upon the combination of state and action. So at any instant, state and action pair, well, that makes things much better than the previous case. And the interesting part, we are using okay dynamic programming. Limitations we have already discussed, but here what we are doing is we are doing something interesting, and that is basically that instead of completing the whole trajectory, can we modify our values in small steps? That means every increment, every small change, can we update my values, my quality values? and that is nothing but that is the temporal difference learning, TD learning, and we use TD learning here. So what is the TD learning? So this is what I want actually. This is the actual value, the current value which is I am having. I find out the difference. This is the temporal difference, and I take the multiply this temporal difference which is here by a value of alpha, which I call as a learning rate, and I add it to my old value, I'll get a new value. This is basically temporal difference learning, and this brings a change in the system, because even if I don't know the complex model or full trajectory, for small parts, I keep on updating my Q values, and I can learn in a much better way. Okay, so there are two methods. One is SARSA method. I'm starting now from the simple one, and now we'll discuss upon the methods, their issues, and then the improvements. So SARSA means basically state, action, reward, state, action. That is basically the meaning of the SARSA. So we have state, we have action, we have new state, we will get a reward, we'll have next action there. And the update equation is here. Okay, so update equation is very simple. This one is basically my goal. This is my target. This is the value I'm getting it. I'll find out the difference between these two, multiply a learning factor, and keep on updating my queue. And once I have all the updates of my queue, I can find out what is the once I have all the values, then I can find out what is the best policy. That means I'll go for argmax on queue. Similarly, we have Q learning method. So Q learning method is again we have state, action, reward, state. But here now you'll find a difference here. I'll put two equations uh, near to each other so that you can compare both the two. What is the difference? See in SARSA what we are doing. What is my target? See on the target. My target is this one. Okay. In Q learning, my target is this one. So we can have I'll go for the max of it. So that's the difference. Okay, so it's not SAR Q. This one is wrong. This one is Q learning. So Q learning is a greedy approach. SARSA is basically kind. It's not a epsilon greedy. It can be a simple kind of approach there. And they have different comparisons and then issues. Like Q learning is off policy. Try to understand why we call it so off policy, because when we say off policy, our learning policy and evaluation policy, they are different. So initially it start with any kind of a random policy, but when update we go for the max. So my learning and my learning and evaluations, they are different. In SARSA, the same random we use in update. This is own policy. So since we are going for max of it here, obviously this will converge a bit fast, but okay, so it's typically faster than than this one. Okay, and then the exploration part is also different here. So exploration and exploitations, we use it here. Those are the parts of how you search the things there. But just for now, we can take it like Q learning update based upon the maximum value, where SARSA update upon whatever the policy is being adopted there. So this is the Q learning, and Q learning is very simple. I told you that we have states here, different states. Okay, so these are the states. You can see S1, S0, S1, S2. Obviously, S5 is not here because it's blocked, and 7 and 11 is not there because they are the terminal states. And each state can take 4 actions going right, left, up, and down. Okay, so what we are doing is we are making this table. We are just making this table the way we have seen earlier. And once this table is ready for us, then okay, we can say if I'm at state S4, so if I'm state at S4, then I'll see that what is the maximum value of S out of these with all the actions, what is the maximum value, and I find that this action value is highest. So there's this action value is highest means going down. So I go down. S4 is S8. So I go to S8. and check it out in asset which one is giving highest value. And it is saying that this is the highest value that is going right. So I'll go right, and likewise I complete my trajectory from this point and I reach it here. This is the sarsa. But the and this is a tabular, oh sorry, this is Q learning and this is a tabular approach. But what is the problem with this? The problem is, say if I have 10,000 or 1 lakh states, and each state can take some actions of say 20 or 100 or likewise, then think of what is the size of my table, and that will create some more problem for my calculations and storage and all that. Well, that is one issue. The second issue is, okay, this works fine if my environment is discrete in nature. So if my discrete in a environment, my states are discrete, actions are discrete, I can easily build up my table. But think of if it is continuous, then how you discretize it? Your discretization, your when you discretize it, your step length can be different than mine and somebody else. So the model keep on getting confusing there. And if it is a continuous, then maybe some value is there which is not in any of the block there, and it's stuck up somewhere. So what is the way? And the way is, can we develop a function for it? That can we develop an approximator function for it? So instead of using discrete stats, can we have a function uh, which is a good approximator? And we know that in machine learning or AI, your neural network is a good function approximator. Okay, this is the solution then. Okay, then we can think of it. We can think of it that how to figure it out. So the Q learning, for Q learning here, the issue we know what is the issue. Otherwise, it will work fine if the discrete steps are less and actions states are less, actions are less. It works fine. But in the real world, this is different, and then we need a function approximator. Say this problem, we need to develop a controller here which controls the height of this wall. Water is coming from up and going out. So how to do it? It's a continuous kind of structure. So the solution is go for a neural network. And what we'll do in the neural network, we take a neural network simple, pass a state to it, okay, and pass action to it, and then okay, it will give me a Q value. So now the Q value, and this one is simple neural network. So no, nothing big to worry on it. Uh, we have certain things we need to understand. And if I'm using neural network, say this is my structure. So I have certain states, and I have certain action. So this is my Q value. Well, this Q value is no more a function of simple S and A. It will also function of theta. Theta means the weights of this neural network. And how you get the weights? Well, we have this some value here. Somehow we calculate error here, and then we back propagate that error, and then keep on updating the weights. That's we do in neural network. So how we calculate the error? So there must be some target. And what is my target? My target is always like this one for optimal Q value. And what I am getting? Well, this one. So this is my Bellman error. So I use this Bellman error to move it back to train the weights. So that's my algorithm. Rest of the things are same. You can see here what is the theta update. So theta, how I do the theta update in simple regressions. If you have done some course on that, my old theta minus alpha times that is a coefficient, learning coefficient, and the gradient value. So this is the gradient over it. So I update my theta. So this is how we do it. Well, when we do it, so this one is we are moving towards a deep Q learning with that is basically neural networks we are using there. But there is a problem. And what is the problem with this one? The problem is, first problem is this one. My data are sequential data. Sequential means state action. They are strongly connected. They are not IIDs. If they are IIDs, then okay, this will work good. because we know that gradient descent algorithm, if you want to do it to find out update your weight, gradient descent will work good if your data are IIDs. So the problem here is my data are not IIDs, so it will create a problem. Then second one is, okay, so the target is always changing. You see here, what is this one? What we are calculating, from where we are calculating Q? We are calculating Q from neural network. Okay, and right, this value always keep on changing because every step you will have a new max of Q value there. So this is not stationary. So if so if you find out, if you want to find out the derivative of a error, it will work good once your target is fixed and one value is only changing. Then you can find out easily what is the rate of change of error. But if my target is also changing, then it is a difficulty, and that leads to instability of the algorithm. So now we have two different challenges to figure it out how to address these two challenges. So people have suggested one thing here. So let's talk about one is IIDs, how to create it. They say that let's create a buffer. Buffer means I perform simple sums. I have state, I take any action, I'll reach to S2, I get a reward. I make such kind of a pairs, and that is basically my experience. I perform this activity, whatever is the experience, I store it. So the storage somewhere is known as your buffer. So this is buffer basically. This is we store the data. And what I'll do now is when I'm going for the training, okay, I'll take some random samples from here. Try to understand it. So if I take random samples from here, they are randomly taken. So I have broken that IID issue from there. And also I'm considering my past experience into my calculation. So that will help us in my better learning. So that is what is being done here. You can see here, initialize here, you create a memory here, D. And from this memory, you take some random samples and some batch of samples, we call it a mini batch, and update it. So now my data, they are independent data. And once we have new value of theta, okay, I'll take it back and put it in my neural network. And whatever the new values, if I'm getting it, I put it into back into my memory there. So that is how I get rid of the first issue. But now the second issue is there. That is basically the stationary. So there we can do some more modifications here. Okay. So in stationary, what we can do is there can be various other ways also. But what we can do is, okay, we can take a neural network. We put another loop there. Okay, so we start one neural network with certain value of theta. We randomly take the samples. We run it inside it. Now, when this internal loop works, it has no connection with the outer world. It keep on running. Then from here, we'll get the new data and keep on running. And after some time, say if we run this outer loop for say 1,000 times. After that, whatever the value of theta, we update the my neural network. So there are two things now which are working. That means there are two networks now. One network, which is outer network, which will update slowly. And then there's another network. Oh, we are short of time. Another network. So I move a bit fast. So another network which move a bit faster. So the network which is moving faster, to that network, the outer network values seem stationary. And that is how we can get rid of that non-stationary issues. Okay, so that is there. Oh, sorry, that is there with the that part. And then people suggest that why can't we get now when we work with those things, we can have two networks. We get rid of the issues of that one. But when we apply on various problems, we find that the the network which we are using, they are overestimating. This is the value which is required. It is actual one, and this is where the network is stabilizing. So there is, you can see all red one, there's a huge difference between the two. And this one is, we call it overestimating. Why it's overestimating? Because my network, when I'm updating it, it only depends upon the maximum value. You just think of that, you have certain parameters and which there is a certain kind of a deviation. And if you focus only on the maximum of it, you will go for overestimation of it. So that is basically the overestimation in the previous model. Then this come out with a solution that, okay, let's have a double learning. So now two independent models there. So what we do is, you can see here, one model is here, red one, the another model is the green one. So this model evaluate it, give the value of action here. Okay, so it gives the action, and this model evaluate this action state pair. So how they train it? This becomes outer becomes stationary, it will update, and then this becomes stationary, this will update. Meaning is, when you are training this one, this model remains here. In the next go, you we shift the red one here and put the queue inside it. So our stationary issues will be there, and this type of arrangement, when the two network, they keep on replacing each other and getting trained, they will give us they will help us in getting rid of this one, and the curve will be now much lower, which is in the blue one. This is double queue learning kind of setup. Okay, so I'm just skipping few of the slides because of the shortage of time, going for some application, because that is more important. Yeah, there are a lot of things to be discussed. So this is one approach, one problem which we have uh, uh, where we have implemented. It's a robotic problem. So the robo is there. So we have agent, that is the robo. Put two cameras here to find out the depth into the image. So stereo vision we have created there. The job is to move from this point to reach to the goal, avoiding these obstacles. So all green are the obstacles. Okay, and also to go for, so it can take in some steps and keep on moving, and it reach here. So not only to reach there, but to follow a minimum or shortest path, so that the energy can be saved. So how to ensure it? So that's how the reward is being designed. So what we don't want to hit any obstacle, so we put a negative, high negative reward for it. We want this one to reach at the red side, we put a positive reward here. Okay, we don't want it to waste much time in the space, so every step is given a negative reward. Similarly, if it go diagonal, it consume more time, we got a negative reward here. So this is how the reward is being taken there. How it will work? It start from this place. Okay, from this place, take the picture of the front, what is the image of that one, and from that it give you the state. How? Now this one is a bit complex, because we have image and it's stereo vision, we can have distance also in information into image. What we do, so to make it light, we have used here CNN. So image is taken, and then we have applied CNN, and we go for state values which are much less complex. So that is basically comes here. So this will give us the state. Once this state goes here, we have used your neural network as the proximity approximator. So this will give us the optimal action. Optimal action can be either go left or go right, sorry, up and down, left, right, or diagonal in any of the direction. So it give one of the action. So say it says that go straight, then the signal comes to robot. There are two motors here, okay, and front is free. So it will generate an equal pulse width for both the motors, so that it goes straight. So it moves straight. Once it, so this is robotic control. So once it moves straight, it reaches to a new state. So in the new state, it will observe if it hit, it will get a negative reward, high negative reward. If it is not hitting, it will get -1. If it reaches to the goal, then it will get a +1. So that is how the reward moves here. And then once it reaches new state, then the new pictures will taken, and this keep on moving. This is how this robot will work. So these are the certain results. More details you can get it from this paper we did long back in 2016. So focus it here. So obstacles are fixed and the robot is moving. Now here it is written epoch. This don't get confused. This epoch is nothing like iteration of your algorithm. This epoch means number of times we move this bot. Meaning is we take a bot, place it move like this, hit obstacle. That is one event. We bring it back, and again it take a different path and moves and then hit. Then again we bring it back. So this is basically that is basically number of the episodes we have taken. So after 20,000 episodes, 20,000 of such experiments, we found that okay, this one is 100% it can avoid the obstacles. This one is two obstacles, four obstacles, six obstacles, and eight obstacles. Then we move to the next one. We make it both dynamic. That is basically obstacles are also dynamic, agent is also dynamic. So just to get a good accuracy, we have to go for 1 lakh episodes, 1 lakh times we have to perform the experiment. And you find that around somewhere around 94% accuracy is there. The last part is random, means the obstacles are coming randomly. So this is how this whole setup works there. Coming to the next part, which is this one, which is more related to the John here, which is energy management of hybrid electric vehicle. So we have two parts there. We know that there is a battery and there's another kind of power generation from a fuel, maybe petrol or diesel. Petrol is the most common. So now we have to decide that when to work on which one. So how RL will work? So I told you that for RL we need observations. So what are the observations we need? Okay, we need observations of what is the state of health of a battery, SOC of a battery, state of charge. Sorry, not SOH, no SOC. I need what is the velocity of my vehicle and what is the acceleration of the vehicle. And then what action I'll take? My actions will be the power of the engine, whether I'm taking it from the from my fuel or taking from the battery. And what is the goal? Goal is basically energy utilization or SOC or health of the battery, or you can choose it accordingly. So that is goal. So how to know? So this one is okay, but we have the key is how to design the reward for it. So reward it can taken here like okay, what is my frictional loss? What is my electrical loss? What is the SOC? I want to maintain it. And from there, obviously, when you combine it, you can say that okay, I want to minimize this thing because I may want to minimize my losses. So, but in RL we maximize the reward, so we have taken negative of it. So this is how we have combined it. And then that's all. Then you can use any algorithm. So we tested on DQN, that is deep Q network, and then DDPG, that is deep deterministic policy gradient. This is policy based method. This one is your value based method. And then we tested on different driving cycles. These are the standard driving cycles which are available, just to check it which algorithm is converging fast, which one is giving a good result, and something like that. So this is how you can manage your map. You can do the energy management of hybrid electric vehicle. So with iterations, with rounds, it keep on updating it itself. You can apply it to motor also, but let's take the last example here, and which is the power, which one is power home management, home energy management, residential energy management system is there. So what we had to that, we have PV, we have inverter, we have load, we use battery. Okay, we have inverter therefore also, and then we have grid. Okay, that's fine. So we can have a power flow. So we can have power flow like this from PV to battery, PV to load, PV to battery, PV to grid, battery to load, battery to grid, and then grid to battery and grid to load likewise. So these are our observations. What are the different power, and what are the different powers which we have? So we have, these are the like what is the power, PV power, what is the load, what is the SOC of the battery, and likewise. And the action is okay. Action is basically the direction of the power flow. That direction will give us that from where power is coming. And what is the goal? Goal is basically reduce the cost, reduce the energy consumption. We also have the value of our daily selling price we have incorporated into the calculations. So where we have done is we put design a reward in such a way so that we will get the maximum profit. Well, what we'll get a maximum profit, but we need to ensure something, and that's ensure something is that power balancing should be maintained. So and it may possible there may be violation and it will give more profit, but we put it a penalty here, very high penalty, negative penalty if there is a violation of the balancing equation. So in this case, it is a bit simple because what we have done here is you can see this figure. We have divided the whole spectrum in half over span. So we discretize it. So there are 48 states there. And each state we have the value of PV, load, and selling price, and likewise. And then action is we know that only few components are there. So the state is the action is also less. So we have used Q learning here, simple Q learning, which I have told you that okay, if this is the state, this should be the action, and then we can have a very simplified version of uh, transferring the power from one place to another. The only the disadvantage is that the discretized is there, where most of the things they are assumed linear, but practically we know that battery is non-linear, loads are non-linear, intermittency may be there because at the solar and all those things there. So those things, if you put into it, we have to go for the higher setup or higher version of it, or more complicated algorithms here. So that is how you can implement to this problem. So I'm over by yeah, I'm over by 5 minutes, but I thank you very much. Now we can have 5 or 10 minutes, some questions from your side so that we can have a discussion over the things.
Okay. Thank you, Professor, for delivering such a nice lecture. Now, audience, anyone having question?